It's my pleasure to introduce today our guest, is Jonathon Schrecengost, who is a product engineer at OLEDWorks in the United States. Jonathon holds a PhD in material science and engineering from Penn State, where he specialized in organic optoelectronics. And now at OLEDWorks, he helps drive innovation in OLED development and their production. We have known Jonathon for a while, since he's an expert user of our simulation software Setfos and Laoss. And today we are very happy to have him here with us, sharing his results on multi-stack OLEDs for automotive, lighting, and micro displays. Thanks a lot, Jonathon. The floor is yours, and we are very happy to hear what you're saying.
Okay, thank you very much for that kind introduction. So I'm very excited today to talk about multi-stack OLED use in automotive lighting and microdisplay applications. On today's agenda is an introduction to OLEDWorks and how our Automotive brand multi-stack OLEDs are used in the automotive industry. I'll then work through a practical example of how an OLED formulation is optimized for an automotive product using Fluxim Setfos optical simulation software. And lastly, I will showcase OLEDWorks microdisplay technology and demonstrate how Setfos can be used to optimize OLED microdisplay formulations. OLEDWorks is a global multi-stack OLED technology leader. We manufacture OLEDs for a variety of applications, such as high CRI, low-profile general lighting products. OLEDWorks has entered the micro OLED display space. We currently offer both WXGA and SXGA resolution microdisplays capable of supporting multiple stacks and being driven to high brightness. OLEDWorks is most known for our Automotive brand automotive products, including our digital taillights that can currently be found on the road in more than 5 Audi vehicles worldwide. OLEDWorks was founded by former Eastman Kodak employees in 2010 with our headquarters in Rochester, New York. In 2015, we acquired Philips' OLED division, which included a top manufacturing facility in Aachen, Germany, where we manufacture the majority of our products today. In 2020, OLEDWorks was selected for 5 automotive platforms by Audi, and we've since continued to innovate and provide brighter and longer-lasting multi-stack OLEDs for automotive products. OLEDs can enhance the experience and aesthetic in a variety of areas on automotive vehicles, such as interior lighting, direct view displays, badging and logos, and on taillights, which will be the focus of this portion of my talk today. Why choose OLEDs over LEDs in automotive taillights? At a high level, LED taillights are either homogeneous or pixelated, but our OLED technology is able to be both simultaneously thanks to the surface emission of the OLED and segmented pixel design. Our OLEDs initially offered minimal segmentation. However, over time, we've dramatically increased the number of individually addressable segments up to 128. This has essentially transitioned our taillights to becoming display-like, improving vehicle-to-everything communication capabilities. You can currently find our taillights in the Audi A8, Q8, Q7, Q6 e-tron, and A5. We continue to innovate and increase the number of addressable segments, along with other other landmark OLED advancements, such as bendable taillights that will allow for an ultra-thin profile to conform to the shape of the car. Here's an example of our digital bendable panels, which I'm always impressed by. Our advanced OLED taillights are capable of producing a variety of animations and displaying symbols and text to improve vehicle-to-everything communication and to improve the overall look and aesthetic of our vehicles. Our OLEDs are ultra-thin, with a total thickness typically less than 1 millimeter. This makes them lightweight and low profile compared to LED counterparts. Our OLED taillights meet rigorous automotive standards, such as high brightness, lifetime exceeding 20,000 hours in operation, and a 15-year lifetime in ambient conditions. They must also operate in harsh temperature conditions from minus 40 degrees C to 105 degrees C. At a high level, adding additional OLED stacks allows us to achieve higher brightness at equal current density. This can dramatically extend the lifetime of our OLED products and enable higher brightness applications, such as a transition from tail light function to stoplight function. I'll now work through an example of how I would develop an amber OLED turn signal with the assistance of Fluxim Setfos simulation software. Step 1 is to identify ideal material combinations for our OLED. Step 2 is to model a basic one-stack amber OLED. Here I show an example of a first approximation of a generic amber emitter. I simulate a map of all optical cavity solutions to generate all possibilities and to select an ideal formulation. I then fabricate this OLED and measure the OLED emission as a function of angle. From here, I can extract a much better intrinsic electroluminescence spectrum for our amber emitter. Here you can see an intrinsic electroluminescence spectrum with a lower energy shoulder fit the data much better. Now that we have an accurate intrinsic electroluminescence spectrum, I'm prepared to model multi-stack OLEDs. Before I begin this process, I consider production constraints to limit solutions to those that are manufacturable. I next consider the goal specifications for a product, which may include color versus viewing angle, brightness, and lifetime requirements. I use these to assess how many OLED stacks are required for a given product. In this example, I may find that a 6-stack OLED is required to meet the brightness target of a turn signal, which is typically around 20,000 nits. And I will filter the solutions that I generate to ensure that they fall within the ECE amber color standard so that the turn signal is a legal color. I then get to fabricate and measure my multi-stack OLED. At this point, remodeling of the OLED may be required if imperfect assumptions were made in the model. Otherwise, the model may be accurate, but coding imperfections may result in suboptimal performance. In this case, I can use my Setfos generated modeling map to point manufacturing in an appropriate direction for quicker optimization. In my experience, Setfos generally reduces the number of experiments by about an order of magnitude compared to a purely empirical approach. This means 10 times faster time to commercialization and at reduced development costs. I'd like to switch topics now and discuss that OLEDWorks has entered the microdisplay industry through a joint development with our friends at Fraunhofer IPMS. We currently offer OLEDs on both WXGA and SXGA resolution microdisplays. Multi-stack OLEDs allow us to be more selective on the composition of emissive layers in our microdisplays, and we manufacture white OLEDs with color filters because we believe this to be a simpler manufacturing process with higher yield and throughput potential. With top-emitting OLEDs, we are able to more strongly tune or detune the optical cavity and emissive layer positions to optimize color gamut, brightness, and viewing angle for products of interest. One such example is daytime augmented reality applications, or AR. High brightness is required for the displayed information to be visible while competing with ambient sunlight. Our monochrome green OLEDs are capable of exceeding 100,000 candela per meter squared. High brightness is also valuable in VR applications in order to lower the duty cycle and reduce motion blur. Each additional stack increases the voltage required to drive the display. This is what makes our SXGA microdisplay so special. It is the world's first high-voltage CMOS backplane capable of being driven to high voltage without loss of contrast. In this example, I show how a 6-stack white OLED display is capable of outputting tens of thousands of nits before color filters are applied. I'll now show an example of how my general approach to developing first a monochrome OLED microdisplay is made easier with the assistance of Setfos. First, I aim to simplify the computational space required to find an optimal solution by simplifying the OLED to a single organic layer whose thickness I will vary. I will also vary the position of a delta function recombination zone that I will sweep from anode to cathode. In this case, I am starting with a simple green emitter, and I'm able to generate a map of all possible antinodes in a variety of optical cavity thicknesses. I can see clearly from the map that in order to make a highly efficient 6-stack monochrome green OLED, that I would need an OLED thickness of around 900 nanometers to have all 6 antinodes. At this point, I'm able to limit my computational space by placing emitters near these antinode locations and sweep parameters using the full NK dispersion of all of the real layers in my OLED formulation. Here I have shown an example of the electroluminescence spectrum of my optimized OLED. Now, full-color multi-stack OLEDs and microdisplays are much more challenging to optimize due to the number of permutations that are possible. My approach is to begin by solving the antinode map solutions for all 3 primary colors of interest, similar to how I just did with the monochrome example. I will recolor the plots to make it easier to see where the red, green, and blue antinode solutions will align. In this example, I can see that there are only 3 OLED thicknesses that yield reasonable overlap for our red, green, and blue emitters that I have chosen. I now show how I might begin to optimize a 3-stack white OLED. I can see that there is good alignment of my 3 colors at a total OLED thickness of around 900 nanometers. I will select an antinode for each color to optimize the full structure using all of the real organic layers. Now, I'd like to give one example of how even more stacks can be added to enhance the performance of an OLED microdisplay based on their intended use. In this example, let's suppose that I am concerned about burn-in caused by the degradation of the blue emissive layer, which is known to be much less stable than its phosphorescent red or green counterparts. I may add more blue stacks so that I can run the blue subpixels at a much lower current density to extend lifetime. Setfos is absolutely key to understanding what options I have when deciding what combinations of colors are available to me. I can see clearly that I can easily add 3 more blue stacks to our previous 3-stack white OLED structure to enhance blue emission. Thank you very much for listening to my talk. I hope that you learned something interesting and that you enjoyed some of the taillight demonstrations and what's coming with Microdisplay. I'd be more than happy to answer any questions at this time.
Indeed, this was a great talk, Jonathon. Thanks a lot. And especially it was great to see that Setfos can be used also in industry. It's something that we don't see that much because most of the time we have academics presenting, and this talk was a perfect explanation how we can use Setfos for industrial applications. Thanks a lot. I can start myself with a question. You've been telling us that you work on a large area OLEDs, small area OLEDs. We have also a lot of requests from people working on micro displays saying that then it's very difficult when the pixels is becoming so small to control the optical crosstalk, optical and electrical crosstalk in these pixels. Do you see anything like that in your prototypes or commercial products?
We do. So I can only disclose so much, of course, of being in industry.
Sure.
I recently gave a talk in Korea in last fall where I discussed some of our optimizations of handling electrical crosstalk and multi-stack OLEDs. So it's no surprise that as you add number of stacks, both optical and electrical crosstalk may increase. And that's an ongoing area of research that we've made a lot of progress in with dramatically reducing electrical crosstalk, especially at low current densities for low brightness applications.
Great. And on the large area, the one that you use for automotive, which are the challenges there? You're saying that now you're increasing the number of segments. Why was so difficult at the beginning to start with this higher number of segments that you have been showing in the last slide?
In general, it has to do with scalability of how complicated the backplane is. So as you increase the number of segments, the design gets more complicated. And so there's a lot of engineering work that goes into being able to have so many addressable segments in such a compressed area.
Mm-hmm. And also, I can imagine that the area should be homogeneous. So the color that is coming out, the amount of light that is coming out from the single OLED should be homogeneous everywhere. And probably that's also a matter of optimization of the resistance of the electrodes and so on, right?
Yes, exactly. So that's unfortunately I didn't include that in my talk today, but we do use Laoss. So I'll do my my sales pitch for Laoss. Laoss has been tremendous for being able to optimize essentially anode bus lines to be able to make uniform segments.
That's great. Let me check if there are questions from the audience. We still have 50 people participating in this talk. At the moment, no one wrote any question. I think the presentation was very clear, but this channel will be open. So everyone that has a question could still write down his or her own question in the chat. And Jonathon, I'm sure, is going to reply later on. So
Of course.
it was a very interesting talk, short this time, but very straight to the point. Thank you very much, Jonathon, once more. And I really hope we will be able to collaborate again. Oh, yeah, there's a question.
Great.
Let's see. They're asking you, they're saying, looking online at OLEDWorks website, if I'm an academic, it reads as if I cannot buy developer kit. Is this correct?
That might be a question for our marketing team, sales and marketing team. If you can email me, I'd be more than happy to connect you with them to clarify that question.
There's another question. What's your target brightness on OLEDs?
Yeah, so it depends on the product. So one of the strengths of OLEDWorks is that we're able to take requests from a variety of customers, and we're able to tune our OLED formulations so that they're optimal for these cases. So for example, sometimes there are brightness requirements based on the product. If I pull this slide up, we can see that sometimes there are legal requirements. For example, for our current tail light function, we need a brightness of at least 2000 candela per meter squared. A typical brightness for a turn or a stop function may be as high as 20,000 nits. Of course, this all varies. And the needs for the microdisplay side can vary tremendously as well. So the approach is not only hitting a brightness requirement, but by adding multi-stacks, we're able to achieve the target brightness at much lower current density, which extends lifetime.
Thanks a lot. And there is another question. How much brightness drop do you see from glass to silicon substrates?
That is an interesting question. I'm going to have to answer it a little bit generally. In general, if you're on a glass substrate, you probably have a more weak optical cavity due to probably only having one strongly reflecting interface and one weakly reflecting interface. One of the advantages of doing things on silicon, for example, you might make a top emitting OLED where you can take advantage of having two reflectors that might enhance OLED emission through basically optical cavity effect, which is all demonstratable in Setfos.
Sure, makes sense. Great. I think, oh, yeah, we are. They want to know a little bit more how the larger simulation tool is helping in the design.
I see. So perhaps I can spend a little more time on this. So to give a more specific example, suppose that this was our real intrinsic electroluminescence spectrum from an amber OLED. I might make certain assumptions, either based on physics that I understand or empirical fits to data that we have. Let me point my laser pointer. So suppose that we have a very simple one-stack OLED where I have an amber emitter. I might have to make certain assumptions about the recombination zone width and location. And then I might use Setfos to optimize its position between essentially the electrodes by varying transport and blocking layer thicknesses. And so I'm able to generate a full list of solutions. And here I have the brightness as a function of basically the layer thickness in each for the hole and the electron transport sides. And in this case, I said, this is one of the brightest solutions, so I'll pick this one. But there are other factors to consider, right? I may need to make sure that the color is in spec with this solution, which I can do with Setfos. I may be concerned about angular dependence, which I can simulate with Setfos. As you begin to add stacks, you begin to add a tremendous amount of potential complexity. So you can imagine that when there starts to become perhaps dozens of layers in my OLED, that there are a lot of different layer thicknesses that one might be able to tune. And perhaps there are trade-offs based on, if there are tremendously different refractive indices, for example, for some of the layers. Being able to consider design, production constraints or other constraints. And of course, the strength of OLEDWorks is that, we don't make materials. We work with industry-leading vendors who supply us with materials, and we essentially use that data to determine what materials were going to work best for an OLED on any given case, whether it's trying to optimize EQE or lifetime. And so that's sort of the basic approach. I hope that answered the question. Maybe I can extend on that a little more. Setfos is also useful for basically quality control. So it might be that I've made poor assumptions in my model, such as the recombination zone location. But it might be that the model is actually very good, and it tends to match up with angle-dependent data. And so in that case, I might make an OLED and get suboptimal performance. And I might use a map like this to suggest, oh, well, the luminance wasn't quite as high as it should have been. Perhaps my tooling factor for a certain material was 2% too high. That would explain why my brightness was a little bit low. And so Setfos is also tremendously useful from that perspective for both asking what I should make and making sure that I've made what I wanted to.
Jonathon, this was amazing. I wanted to say that we didn't pay you for this. It's amazing that you gave us such a nice presentation about our products. I'm very much impressed. I think I explained myself a little bit. Let me read it. Yeah. There was a little bit of a misunderstanding when I formulated my question, because they were asking about the large area simulation tool, so basically Laoss, but probably I can quickly reply by saying that Laoss allows you, to, for example, in this picture, to optimize then the electrodes to make sure that the electrode itself is suitable for this kind of geometry. There are no losses because, as we know, on such a large area, the parasitic resistance, the resistance of the electrode, will play a big role in order to make sure that for example, every pixel is homogeneous, is having the same emission. Then Laoss is affecting in this regard, right? There is another question here. Thank you for the engaging presentation. I'm not sure if this is something you're able to elaborate on, but with regard to commercial applications, could you share how the thin films are fabricated? Are techniques such as spin coating, evaporation, or a combination of both employed? Additionally, how manageable is to ensure homogeneity across the films?
Yes, so I have to be, careful with what I'm able to disclose.
Sure.
There are many ways of fabricating OLEDs, whether it's, some people might use spin coating. Thermal evaporation is much more popular in industry. And so maybe I'll leave the question at that, if that's satisfactory.
Understood. Thanks a lot again, Jonathon. This was great. It was enough. And I would like to thank everyone that attended this webinar. We don't have a title for the next one, but soon you will receive an email from us. This is going to be in 1 month from now. Thanks again, you and everyone, and I will see you soon. Bye.
Thanks, everyone.
Bye-bye.
Thanks, Jonathan. Bye-bye.